Hi, my name is Vian Stipp, and I'm a machine learning research engineer based out of San Francisco. And today we're going to deep dive into the paper STaR, the self-taught reasoner. So, what are LLMs missing? So, we know that human decision making is often made by firstly breaking down a problem into its subcomponents, thinking about each of those in detail, with multiple cycles in our brain before assembling an answer together. LLMs don't seem to do this. They seem to just directly via a chain of associations just jump into an answer without considering or breaking it down. And Daniel Kahneman introduced System 2 versus System 1 thinking in his popular book, Thinking Fast and Slow, in which he describes, System 1 as being this associative, fast, 95% of our cognitive processing thinking, versus System 2, which is suited for more complex problems, problems that we can't just directly react to, but really involves a conscious process of us reasoning through it slowly. LLMs seem to be more towards the System 1 side of things, if we were to draw that analogy. And so there's been various attempts to try to architect or instill this System 2 like thinking into LLMs. And a couple of these papers have been the chain of thought paper, the show your work Scratchpad paper, and the tree of thought paper, building on those. And this looks like explicitly instructing the LLM, let's think step by step, giving it a Scratchpad to show it's working, or using a tree of thoughts. And in all of these techniques, essentially the idea is to slow the LLM down, to have it reason about its answer or give rationale before predicting the final answer. And these methods seem to actually increase the accuracy of an LLM, especially in these complex situations. So let's have a look at what is a rationale generation and what is rationalization. So we can see here that we've got a question and an answer from the paper, from the STaR paper, and the question is, what are people in a library likely doing? So an LLM could be instructed in one scenario just to directly give an answer. But we'll see that this is something that it's typically it will have higher error rates versus if we first ask it to give a rationale. So the rationale can be seen here at the bottom. So we can, if we ask it for a rationale first, it will say, the people in the library are probably studying books. Therefore, the answer is study books. And you can see that this is actually quite tautological, the reasoning it's giving, but it even that still helps increase the accuracy of the answer. So what is the STAR method? So the STAR method consists of sort of two main parts. And the idea is, instead of directly, just prompting the model to give a rationale before it gives its answer, what we're going to try to do is fine tune the underlying language model on those rationales, in particular on the good rationales. And what I mean by a good rationale is one that ends up leading to the correct answer. So suppose we have some data set X and its answers Y. What we can do is use a language model, as you can see in the middle here, a language model to generate rationales. If that rationale ends up leading to the correct answer, then what we can do is we can add that to a database of question, rationale, answer, and we can start fine-tuning the language model on those rationales. However, this is good, and this will actually improve the rationales and the answers of the model, but it will never help the LLM predict the answers that it was getting incorrect, because we'll never end up having rationales that lead to the correct answer. So what we can also do is we can find the rationales that give the incorrect answer, and then we can do what's called rationalization, or otherwise known as kind of post-rationalization, where given the answer, you then go back and generate the rationale. And because the model's given the answer, it's now much easier for it to give a reasoning that would lead up to the correct answer. Then given that rationale can now also be added to the same database of question rational answer. So it's quite a simple algorithm, and all that we need is we're assuming that we have some data sets of inputs and outputs for whatever problem we're trying to solve. And we're also going to assume that we have some, let's say, 10 rationale examples of how, given X, you get to Y. And those are going to be used as few-shot prompts. So what we do is we just start with the initial model and we copy that to M0. And now we're going to do a loop of rationales, fine-tunings, and then further rationale generations until we either converge or we hit a certain number of steps. So step one is given our model, we're going to generate some rationales. So this can look like, given X, where X was, what do people do in a library, or whatever the question was. The rationale going to be generated is, people in a library are probably studying, and studying involves, books. So therefore, they're probably reading books. So that's an example of a rationale. If it ends up getting to the correct answer, then what we're going to do is we're going to add it to this data set. But let's suppose that it actually got the incorrect answer, and it said, people in the library are probably, hungry, so they're eating. That's the incorrect answer. And so what we're going to do is we're going to give the model a hint and say, what do people do in the library? Hint, the answer is they're reading books. Please generate a rationale for this. And it will say, oh, okay, people in the library are probably studying, blah, 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 and so on until it gets the correct answer. And then, because we now have the correct answer and we have a rationale as to how to get from X to that correct answer, we can also add this to the data sets Y, the data set DN. And here in the paper, they've separated it out. We're going to have D and D rationale. And here we just take the union of those. So the model doesn't know which rationales have been generated through rationale generation versus the post rationale generation. And given that new data set, we can actually just now fine tune our model. They used GPT J in the paper, which is a 6 billion parameter language model, but now you can use the models. Llama 3.1 would be a good example. And then you can fine tune that model. Remember, this is fine tuning, just standard next token prediction with teacher forcing to generate a new model MN actually in this case. So after we've done this, what we can do is we can use this new model again to, in the next iteration, generate rationales. The hypothesis being that this model is going to be better at providing rationales than the previous generation of model because it's been fine-tuned on rationales. And then we repeat this process. One thing to note is this model that gets fine-tuned is the original model M. This is not MN minus 1. Because otherwise the data is going to end up having autocorrelation, and it's not going to be IID. In pretty much every ML language model training, the data is assumed to be IID between samples, and so we need to just train the original model from scratch. Just the data set's going to be increasing each time. Or it's going to be increasing in quality each time with each model iteration. So in the paper, they make this interesting claim that STAR can be seen as an approximation to an RL-style policy gradient objective. So what does this mean? Um, so suppose that we know that in STAR we're fine-tuning the model over the rationale and the answer. Um, but suppose that we think about this in RL way, and in particular we suppose that we give reward on the indicator function where y hat, the generated answer, equals to the actual answer y, and we're giving reward when the correct rationale leads to the answer or the correct answer, and we're giving basically a reward of 0 when it doesn't. So that's what this function j is here. J is sort of the policy of the agent, and j is the reward, the total reward expected under that policy. So you would get higher reward for rationales that end up leading to the correct answer more often, and so you'd have a higher expected j. So in policy gradient methods, what you do is you parameterize the policy of the agent, and then you derive the total or expected discounted rewards under that policy, and then you use stochastic gradient descent to maximize that total expected reward. And so what they're claiming here is if we think about the rationale as kind of a latent variable, and we'll talk about that in a second, then you can see this fine-tuning under STAR as an approximation to the RL policy gradient objective. So let's see, first of all, how we can think about this as a latent variable model, and then secondly, we can look at how we go from this to this. Okay, so in the top left is the policy gradient theorem. We'll come onto that in a second. But first, let's just revisit latent variable models. So an example of one is a variational autoencoder. There's another video for that if you're interested. But in a latent variable model, you essentially suppose you just have data x. You model this as being generated by some prior distribution z, and suppose you wanted to write down what's the probability of x under parameters theta. This is simply the integration over the joint distribution of x and z over all values of z, and equivalently that can be written down as x given z weighted by probability of z. And that's making use of the graphical model here. So let's see how we can think about STAR as doing something very similar. So we have our prompts x, and suppose that instead of directly modeling that x generates y, we also model that x generates a rationale and y is jointly generated by the rationale and x. So this is the model that we can now consider that by generating y, you actually first sample a rationale, and then you after sampling the rationale, you can generate y. So now let's look at how that relates to this and this. So you can see that here we're considering that we're actually sampling, given x, a rationale and an answer, which is what this probabilistic graphical model is showing us here. So given x, we're sampling r and then y. So under such a model, let's see how this relates now to the RL policy gradient objective. So I'm going to, just for simplification of the symbols, I'm going to ignore the index I, and I'm just going to look at, how do we go from this to this? And we're going to start with taking the gradient under the parameters of the expectation of R and Y sampled by the model, which is the model M under this in this case. So we sample these and we're looking at the expectation under this sampling, and I keep accidentally adding in the i's. Let's get rid of that. So remember, the indicator function is basically the reward, and now we want to take the gradient of this expectation. So let's firstly write it out, the expectation as its definition, which is going to be the sum over, let's say there's k rationales. This could be an integration as well. I'm just going to write it out as discrete rationales. And so that we have the joint probability of, and these should be hats, r hats, y hats, given x, multiplied by the indicator function. Okay, so, and what we can do now is take the gradient symbol inside. And after this, we can now use a trick and multiply the by 1 essentially, but we're going to multiply by the probability r hat and y hat given x. So not the gradient of it, but just it on its own. That is, we're going to multiply by just pm r hat y hat given x. And you'll see why this helps us in just a second. So now that we have this, we're going to use the log derivative trick. And the log derivative trick says that this gradient over itself, so basically the gradient of the probability of r hat and y hat given x over just the probability of r hat and y hat over x is equal to the log of the gradient of the log of this. So what we can do now is just rewrite this as multiplied by the log of this object. And we can actually see now that what we've derived here is exactly this, and I just need to multiply by this indicator function again. But it's exactly what we set out to do, because this is now an expectation over r hat and y hat. So we've gone from and derived now this how you get the gradient of j, which again, j, remember, is the total reward if we think about this as an RL thing. And now if you also just look at the form or the structure of this equation, if we think of this as the reward, this is now just the gradient of the log of the policy, which relates directly to the policy gradient theorem up here, where you can see the reward here and the policy gradient. So this is now very closely connected to STaR, and you can think about STaR, when we're fine-tuning this. What we're doing is we're greedily sampling, because we're firstly taking out all of the samples that don't lead to y hat, where y hat equals y, but also we're using teacher forcing because it's a fine-tuning method. And so this is now very closely connected to the RL objective. If we didn't do greedy sampling, This would look something perhaps more like RLHF, where you sample the full trajectory before you give the reward. But in this case, it's like doing a greedy version of that. So let's have a look at some of the experiments. So they fine tune using STaR on a couple of different data sets. There's arithmetic, common sense QA, otherwise known as CQA, and a grade school math data set, GSM8K. So on CQA, for example, we see that STaR with rationalization substantially improves over just directly fine-tuning a GPT-J model on it, going from 60 to 72. And even without the rationalization, where the model isn't being fed the post-rationalization from giving the answer hint, and also fine-tuning on that, even without doing that, you get a substantial boost. Even more impressive is the performance on the grade school math data set, going all the way from 5.8% on the test set to 10.7. So we can see that this technique clearly works on multiple data sets. So now that we've talked about the STaR paper, and we've seen that by using a model to generate rationales, this is something closer to System 2 thinking, and it increases the accuracy of large language models in giving an answer. However, what's next, or what are some other research or some other steps that we can take to further improve on this? So there's been a lot of talk recently about some of the problems of large language models, and furthermore, this idea of the one-step trap, which was a recent tweet by Rich Sutton, in which he describes models that need to just by their design predict something far out into the future using an increment or a very large amount of incremental steps, and criticizing these models as essentially being doomed, similarly to Jan LeCun here. Large language models fall into this class because they're having to predict one token at a time, and they're not planning in some high level abstract space before decomposing that into tokens, but they're directly planning something using tokens. The STaR paper, of course, also is planning in token space. Jan LeCun's argument is that the probability of something being correct essentially drops to zero the longer that sequence. And he says that this is not fixable. So his proposal is joint embedding predictive architectures, or JEPA, in which the model is planning in representation space, and where the representations of planning and of prediction can be layered hierarchically. So one classic example of human planning in a hierarchical sense is, suppose I want to fly to Paris. I don't immediately start making decisions and actions based on very low level movements of my body, my fingers. But what I end up doing is breaking that problem down hierarchically, saying, okay, first I need to buy an aeroplane ticket, then I need to get in the car, drive to the airport, and so on. And each of these subtasks or sub goals is in turn hierarchically broken down somewhat recursively before I actually execute on those. And JEP is one framework or one line of thinking along that. Jürgen Schmidhuber as well has been working on subtasks and subtask sub-goal discovery within reinforcement learning as an approach to directly mirror what's maybe happening in a human brain. But in summary, all of these methods are about planning in abstract or planning in representation space, versus STaR, which is planning somewhat in token space. So some further resources. Firstly, William James coined the stream of thought consciousness. back in 1890. And if you're more interested in the psychological aspect and the foundations of psychology, then William James, the father of American psychology, is worth reading. Thinking Fast and Slow is also a great popular book for bringing an analogy to language models and thinking about how to implement some of that psychology into them. And then furthermore, there's some of the papers that came before the STaR paper on rationales, also related to few-shot prompting of LLMs. Thank you. Bye.